Hello students, welcome to the course on Advanced Digital Communication and the course code is MCE 102. This is the course for MTech EC first semester students. Myself, who is the course coordinator of this course, is Dr. Surajit Bosak, is an assistant professor of EC department, Guru Nanak Institute of Technology, Kolkata. And this is my official email address. Today, we are going to start lecture number 6 from the baseband signal receiver and probabilities of bit error. And the topic for today's discussion is QPSK, quadrature phase shift keying. That is the signal space vector approach to calculate probability of error in QPSK. And the lesson objective of this topic is analyze signal vector representation of various digitally modulated signals by creating signal constellation and compute the bit error performance. And this topic is mapped to CO number 2. So let us start lecture number 6 with the topic of quadrature or quadri-phase shift keying, which is abbreviated as QPSK. So the provision of reliable performance exemplified by a very low probability of error is one important goal in the design of a digital communication system. Now, another important goal is the efficient utilization of channel bandwidth. So, in this subsection, we study a bandwidth conserving modulation scheme, which is known as coherent quadri-phase shift keying, which is an example of quadrature carrier multiplexing. So this is the importance of QPSK system. So in quadri phase shift keying or QPSK, the information carried by the transmitted signal is contained in the phase. In particular, the phase of the carrier takes one of four equally spaced values, such as pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. For this set of values, we may define the transmitted signal as SIT equal to square root of 2e by t cos 2 pi fct plus 2i minus 1 into pi by 4, where t belongs to 0 to t. Otherwise, it is 0. Now here, I equal to 1, 2, 3, 4. And E is the transmitted signal energy per symbol. And T is the symbol duration. The carrier frequency Fc equals Nc by T for some fixed integer Nc. Each possible value of the phase corresponds to a unique die bit. Thus, for example, we may choose the foregoing sets of phase values to represent the gray encoded set of die bits, that is 10, 00, 01 and 11, where only a single bit is changed from one die bit to the next. So the signal space diagram of QPSK. Using a well-known trigonometric identity, we may use the earlier expression, that is this expression, to redefine the transmitted signal SIT for the interval t belongs to 0 to capital T in the equivalent form SIT equal to square root of 2e by t cos 2i minus 1 into pi by 4, just cos A cos B minus sin A sin B into cos 2 pi fct minus square root of 2e by t sin 2i minus 1 into pi by 4 into sin 2 pi fct, where I equal to 1, 2, 3, 4. Now, based on this representation, we can make the following observations. What are the observations? There are two orthonormal basis functions, phi 1 and phi 2t, contained in the expansion of SIT. Specifically, phi 1t and phi 2t are defined by a pair of quadrature carriers, where phi 1t equal to square root of 2 by t cos 2 pi fct, where t belongs to 0 to capital T, and phi 2t equal to square root of 2 by t sin 2 pi fct. So these are the two orthonormal basis functions. And there are 4 message points and associated signal vectors are defined as Si equal to square root of E cos 2i minus 1 into pi by 4 and minus square root of E sin 2i minus 1 into pi by 4, where I equal to 1, 2, 3, 4. So the elements of the signal vectors, namely say Si1 and Si2, have their values. So for the die bit, say 10, 00, 01 and 11, and the correspondingly phase of the QPSK signals in radians, they are pi by 4, 3 pi by 4, 5 pi by 4 and 7 by 5 pi by 4. And accordingly, you can calculate the coordinates of the message points. Say SI1 equal to integration of 0 to TB SIT phi 1t dt. So in that way, you can calculate the coordinates of the message points. And for 10, it is plus root over E by 2, and for SI2 is minus root over E by 2. For similarly for 00, SI1 is minus root over E by 2 and SI2 is minus root over E by 2. And correspondingly for 01, SI1 is minus root over E by 2 and SI2 is now plus root over E by 2. And for the last gray encoded input die bit, that is 1 1, SI1 is now become a plus root over E by 2, and SI2 is plus root over, again plus root over E by 2. So these are the coordinates. Now accordingly, you can draw the signal space diagram of coherent QPSK signal. See, there are two basis functions, orthonormal basis functions are present, which are phi 1 and phi 2. Now for message point M1, that is the first 1 0, phase shift is pi by 4, and this is plus E by 2 SI1, and SI2 is minus root over E by 2. Now we are considering this negative phi 2 axis is the positive, that is the downward direction is the positive phi 2, and upward direction y axis is the negative phi 2. So message point 1 exists in this region 1 0. Similarly, if you plot the message point 2, that is 0 0, and message point 3 M3, that is 0 1, and message point M4, that is 1 1. So these are the 4 message points you can easily draw according to these coordinates and phase angle. So this is the signal space diagram of QPSK signal. Okay. Now draw a QPSK waveform, time domain waveform. Suppose the input binary sequence is 0 1 1 0 1 0 and 0 0. Now you have to draw its corresponding QPSK modulated signal. So first you have to, as we know that QPSK transmits like a die bit. So odd number sequence polarity of coefficient, say SI1 into phi 1t. So these are, say 0 1, odd number 0, first start, it will start from 0, then 1, then again 1, this 1 and this 0. So see 0 1 1 0, and correspondingly we draw from 0 to 1 there is a phase shift of 180 degree, then again from 1 to 0 there is a phase shift. Now for even number sequence, say SI2 into phi 2t, even number of sequence. Now even number means it is multiplied with phi 2t means sine. SI1 is multiplied with cos signal, phi 1t means it's cos, and phi 2t means it is multiplied with sine k, sine 2 pi fct. So now that is why sine 0 is 0, so it start from here, and the bits are correspondingly these 1, then 0 0 and 0. See 1 0 0 0. So first 1, then phase shift, and then all are the zeros. Now ST equal to SI1 into phi 1t plus SI2 into phi 2t. So and correspondingly we get the signal is like that. See, and another important thing is that from 0 1 to 1 0. Now from 0 1, that is here, from 1 0, 0 1 to 1 0. So there is a phase shift of how much phase shift? From 0 1 to 1 0. 0 1 means pi by 4, 5 pi by 4 to 1 0 pi by 4. So it is pi. Pi by 4 minus pi by 4. So it is now pi. Because here is 45 degree, 45, 90 degree, and again 90 degree. So total is 180 degree. So 01 to 10, there is a phase shift of 180 degree. And here again 10 to 10, there is a new phase shift, and then 10 to 00. So this point is 10 to 00. So that phase shift is 90 degree. 10 to 00. See again 10 to 00. So that is 2 pi by 4. That is pi by 2. So from 10 to 00, there is a phase shift of pi by 2. So in this way, you can draw the QPSK waveform, modulated waveform. Now, error probability calculation for QPSK. In a coherent QPSK system, the received signal xt is defined as xt equal to SIT plus WT, where t belongs to 0 to capital T and I equal to 1, 2, 3, 4. Where WT is the sample function of a wide Gaussian noise process of 0 mean and power spectral density in 0 by 2. So correspondingly, the observation vector x has two elements. One is x1 and other is x2, and which is defined by x1 equal to 0 to capital T xt phi 1 t dt, and you know the value of xt, that is square root of, if we integrate it, then we can get, because you know about the value of this SI, square root of this. So if you, after putting this, now becomes square root of E cos 2i minus 1 into pi by 4 plus W1. So now this is now plus minus square root of E by 2 plus W1. And similarly, x2 equal to 0 to t xt phi 2 t dt. So minus root over square root of E sine 2i minus 1 into pi by 4 plus W2. So that is now minus plus square root of E by 2 plus W2. Now what is the decision rule? Okay, thus the observable element x1 and x2 are sample values of independent Gaussian random variables with mean values equal to plus minus square root of E by 2 and minus plus square root of E by 2 with a common variance equal to n0 by 2. Now the decision rule is now simply to decide that S1T was transmitted if the received signal point associated with the observation vector x falls inside region Z1. Decide that S2T was transmitted if the received signal point falls inside region Z2, and so on. An erroneous decision will be made if, for example, signal S40 is transmitted, but the noise WT is such that the received signal point falls outside region Z4. So, to calculate the average probability of symbol error, that a coherent QPSK system is in fact equivalent to two coherent binary PSK system working in parallel and using two carriers that are in phase quadrature. This is merely a statement of the quadrature carrier multiplexing property of coherent QPSK. The in-phase channel output X1 and the quadrature channel output X2 may be viewed as the individual outputs of the two coherent binary PSK system. So the signal, thus according to expression 6 point, that is the two expression, that is X1 and X2, these two binary PSK systems may be characterized as follows. That is, the signal energy per bit is E by 2 and noise spectral density is N0 by 2. Therefore, for the average probability of bit error of a coherent BPSK system, we may now state that the average probability of bit error in each channel of the coherent QPSK system is P dash equal to half ERFC square root of E by 2 into N by N0, which is half ERFC square root of E by 2 N0. Now, how to calculate the average probability of bit error in two channel for coherent QPSK system? Another important point to note that the bit errors in the in-phase and quadrature channels of the coherent QPSK system are statistically independent. So the in-phase channel makes a decision on one of the two bits constituting a symbol, that is a die bit of the QPSK signal, and the quadrature channel takes care of the other bit. Accordingly, the average probability of a correct decision resulting from the combined action of the two channels working together is PC equal to 1 minus P dashed whole square, that is 1 minus half ERFC into square root of E by 2 N0 square. So it now becomes 1 minus ERFC square root of E by 2 N0 plus 1 by 4 ERFC square E by 2 N0. So the average probability of symbol error for coherent QPSK system is therefore PE equal to 1 by 1 minus PC. That now becomes ERFC square root of E by 2 N0 minus 1 by 4 ERFC square root of E by 2 N0. Now in the region where E by 2 N0 much greater than 1, that is high SNR assumption, we may ignore the quadratic term on the right hand side, this term. So we approximate the formula for the average probability of symbol error for coherent QPSK system is PE equal to ERFC by 2 square root of E by 2 N0. Now the formula may also be derived in another insightful way. using the signal space diagram. Since the four message points of this diagram are circularly symmetric with respect to the origin, we may say PE less than or is equal to half into summation of k equal to 1 to 4, where k not equal to I, ERFC dik by 2 square root of n0. Now consider, for example, message point M1 corresponding to die bit 10 chosen as the transmitted message point. The message points M2 and M4 corresponding to die bits 00 and 11 are the closest to M1. So from figure 6.6, we readily find that M1 is equivalent from M2 and M4. In a Euclidean sense, as shown by D12 equal to D14 equal to square root of 2e. Now assuming that E by N0 is large enough to ignore the contribution of the most distant message point M3 corresponding to die bit 01 relative to M1, we find that an approximation expression for PE that is same in the expression, that is this expression, probability of ERFC, this expression. Now note that in mistaking either M2 or M4 for M1, a single bit error is made. On the other hand, in mistaking me M3 or M1, 2 bits error are made. Now for a high enough in a E by N0, the likelihood of both bits of a symbol being an error is much less than a single bit, which is a further justification for ignoring M3 in calculating PE when M1 is sent. Now in a QPSK system, we note that since there are 2 bits per symbol, the transmitted signal energy per symbol is twice the signal energy per bit. That is E equal to 2 into EB. Thus expressing the average probability of symbol error in terms of the ratio AB by N0, we may write PE equal to ERFC into square root of EB by N0. Now with gray encoding used for in the incoming symbols, we find that the bit error rate of QPSK is exactly PE equal to half ERFC into square root of EB by N0. We may therefore state that a coherent QPSK system achieves the same average probability of bit error as a coherent binary PSK system for the same bit rate and the same EB by N0, but uses 1/2 the channel bandwidth. So the average probability of bit error for QPSK system is exactly identical for the as coherent BPSK system. Okay, so this is the error probability of coherent QPSK system. So let us stop here. Thank you so much.